Alrighty, ladies and gentlemen, we're going to do a little review of all the radicals that we need for our unit test here. So the first thing we're going to start off doing is simplifying some radicals. There are an awful lot of things that you can see when you simplify radicals, so I'm not going to be able to show you everything, but I'll show you most of the main ideas that should get you through most of the problems here. So the first thing is, when you see a square root, what I like to do is I like to make a factor tree. So if you give me the number 104 under a radical, I'm going to divide out 2's as many times as I can. And when I do that, I got 2 and 13. So I'm going to write 104 as 2 times 2 times 2 times 13. And x cubed is x times x times x. So when we talk about square roots, a square root is every two numbers underneath a square root, one of them will come out. Let me explain why. 2 times 2 is 4, and the square root of 4 is 2. So this is called a perfect square, and when you make a complete factorization, it helps you find any perfect squares. For every 2 underneath of them, one of them will come out, because the square root of 4 is 2. And this is 4, so a 2 is coming out, and the square root of x squared is x. Now, what's left underneath there is anything that didn't get circled. So a 2 and a 13 and an x. 2 times 13 is 26, and then there's one more x. So when you take the square root of 104, you're going to get 2 radical 26, and the square root of x cubed is x radical x. That is completely simplified. I'm going to do the same thing for this problem. 3 radical 48 is 2 times 24, which is 2 times 12, which is 2 times 6, which is 2 times 3. Now, if I have any pairs, they can come out. So this is 4, and the square root of 4 is 2. So that's going to be one of the 2's on the outside. I have another 4 underneath, so another 2 will come out. And what's left is a 3. It's important you know that what is on the outside is going to get multiplied. So 3 times 2 is 6, and 6 times 2 is 12. This is 12 radicals. The cool thing about these problems is if you're simplifying radicals, you can very easily check them with the decimal version. So 3 radical 48 is 20.78, and 12 radical 3 should also be 20.78. And it is, so I know we did it right. This would never get you credit on the test, but it does help you check your answers. Let's try another one. This is distributive property. So 2 has to get multiplied by radical 3. Well, that's just 2 radical 3. This is on the outside of a radical. This is on the inside. They don't play nice. Minus. Now, this is radical 3 times 12. But I'm not going to multiply 3 times 12 and then have to break it down. Let's just go ahead and, even though that would be handy in this problem, let's factor 12. 12 is 3 times 4, which is 2 times 2. Now, there's nothing you can do with 2 radical 3. That's 2 radical 3. But in this problem, you're like, wait a minute, 3 comes out and a 2 comes out? Well, that's going to give you 6. Why does that happen? Oh, yeah, 3 times 12 is 36, and the square root of 36 is 6. There's another rule in radicals that says you can never have a radical in the denominator. This is called rationalizing the denominator. The square root of 6 is irrational. We don't like dividing by irrational numbers. So we rationalize it by, I say, giving him a buddy. If you give him a buddy in the denominator, radical 6 times radical 6 is radical 36, which is just 6. But you can't just multiply the bottom of a fraction by something, so you have to also do it in the top. So this is now 5 radical 6 over 6. You should try and factor 6, but 6 is 2 times 3, so there's no pairs in there, and so you can't reduce 5 over 6. You're done. But there are other things that can happen in those problems, so you got to be careful. Let's keep going. This one's pretty tricky. We're going to need to distribute, but it's a quantity squared, so I'm going to write it out twice. This helps me remember that I need to FOIL. Radical 2 times radical 2 is 2. 3 times radical 2 is 3 radical 2. You have another 3 radical 2. And 3 times 3 is 9. So now we look for any like terms. 2 and 9 are both like terms. 2 plus 9 is 11. And then these are also like terms. You see how they have the same radicand? That's the part underneath the square root. So since they have the same radicand, you can combine them. If you have 3 radical 2's and you add 3 more radical 2's, you have 6 radical 2's. The most important thing that you take from these problems is that you absolutely cannot distribute an exponent. You cannot just say, oh, this is going to be radical 2 squared, which is 2, plus 3 squared, which is 9. You'll miss the middle 2 terms. Those 2 terms are part of the problem. We've talked about this a bunch. Just make sure you actually FOIL. You should have 4 multiplications if it's a binomial squared. We have more like terms in this problem. These are both radical 6's. So if you have 5 radical 6's and you take away 3 radical 6's, you're going to have 2 radical 6's. Here we have a product, so radical 5, 5's prime, and I'm just going to make this one big radical, but I'm going to factor 50. So 50 is 25 times 2, which is 5 times 5. So 5 times 5, 5, 2. 5 times 5 times 2. And now I look for pairs like I've done before. That 5 can come out because the square root of 25 is 5, and underneath I still have 10, so 5 radical 10. One more rationalized problem. You give your radical 8 a buddy, and you have 8 radical 8 over 8. Now, sometimes you get lucky here and say, hey, 8 over 8, that's 1. So this is just radical 8, right? It is radical 8, but radical 8 is not simplified. Radical 8 is 2 times 2 times 2, which is 2 radical 2. So the only acceptable answer here, this is completely reduced, is 2 radical 2. That's it for simplifying. Let's try some solving. When you solve, the most important thing is that you isolate the square root first. Here, this is the only thing on one side of the equation, so I can undo square rooting by squaring both sides. Now, on the left side, if I square a square root, I get what's called the radicand. That's the part underneath the square root, so just x minus 3. And on the right side, 4 squared is 16. Now it's a one-step equation. Add 3 to both sides, and you get x equals 19. Now, when you solve radical equations, it's possible that you get what are called extraneous solutions. So it is extremely important that you check your answers. So you need to go back and type in 19 minus 3. 19 is x, we think. And 19 minus 3 is 16, and the square root of 16 is 4. So, okay, yeah, that's good. 19 works. But it won't always work, and even if you solve the equation correctly, you might end up creating those extraneous solutions. Let's try another one, see if that happens. The square root is isolated, so square both sides. And now I have x squared equals, on the right side, 5x plus 6. Now, you see that you have a square term and you have a linear term. That means you know you're going to have to factor or use the quadratic formula. So let's get everything on one side. I'm going to subtract 5x, and I'm going to subtract 6 on both sides, and that gives me this. Now I'm factoring. So I need to find numbers that multiply to the product 1 and negative 6. So 1 times negative 6 is negative 6. I need numbers that multiply to negative 6. I need a pair of numbers that multiplies to negative 6 and adds to the middle. The middle here is negative 5. This is called split the middle. There's lots of ways to factor. This is just how I show you. So the two numbers that do that, what multiplies to negative 6? 1 and 6, 2 and 3. Which ones add to negative 5? There you go. 1 and negative 6. So x squared plus 1x minus 6x, and then I have a minus 6 equals 0. So these two numbers go right there. It's called split the middle because you take this middle term and you split it into two numbers that meet certain criteria. Then you're factor by grouping, so you find the GCF of the first half, which is x, and you have x plus 1. Bring down the minus sign. Right side you have a GCF of 6, but it's really a negative 6, so that's why this is going to be a, oops, I forgot my x. This is going to be an x plus 1. And think about if you distributed back, you'd have negative 6x and then minus 6. That's why this has to be a plus sign. Another way to do it would be say, what's negative 6 divided by negative 6? And that's positive 1. If these match up, you should be feeling pretty good about it. If they don't, you probably did something wrong. So one of my factors is that shared binomial. That's the GCF of x plus 1. And the other is x minus 6. This is just factoring, and you can maybe do this in your head, but I'll work it out for you. Now we got to go back and say, when does this factor equal 0? What plus 1 is 0? That would be negative 1. And what minus 6 is 0? That would be positive 6. So I'm going to erase that because it's bothering me. X equals 6. Now these are two potential answers. But like I said before, you need to check them both. So I'm going to go back up to the original equation, and I'm going to try negative 1. So I'm going to plug that in and say, does negative 1 equal the square root of 5 times negative 1, 5 times negative 1 plus 6? And does 6 equal the square root of 5 times 6 plus 6? We have to check both answers. So let's see, negative 1 equals 5 times negative 1 is negative 5. And that's the square root of 6 minus 5 is 1. Wait a minute, the square root of 1 is 1? That doesn't equal negative 1. This is an extraneous solution. I'm going to show you on the graph in a second, but let's check the other one. 6 equals radical 30 plus 6, which is radical 36. Hey, 6 equals 6, so that works. So x equals 6 works, and x equals -1 is called an extraneous solution. I'll spell that out for you. We'd say x equals -1 is extraneous. Now the easiest way to make sense of this, because this is kind of tricky, is to graph it. So x equals radical 5x plus 6. So I'm going to graph that in Desmos. I'm going to graph it as if it were a system of equations. X and the square root of 5x plus 6. So we can see that at 6 they do intersect, x equals 6. But why don't they intersect at -1? Well, our algebra essentially treated this square root as if it was a parabola. But it's not actually a parabola. Oops. Negative square root of 5x plus 6. That keeps showing up. Okay. So if it were a whole parabola, then it would intersect at -1. But our original equation wasn't actually a parabola. See, we solved a quadratic here, but we didn't really have a quadratic. We only had half of a quadratic. So this solution doesn't actually solve our original equation. So we only have one solution here, and it's at x equals 6. And it happens that y also equals 6. So that's cool, I guess. The only answer is positive 6, and -1 is said to be an extraneous solution. Let's try a couple more. Here we have square roots on both sides, so I'm going to square both sides. And on the left side, I have 2x minus 7. And on the right side, I have 4x plus 13. So all the radicals go away. Now it's just a multi-step equation. Let's get all of our x's on one side. 2x plus 13. Oops. And then we'll also subtract 13. And -7 and -13 make -20. And then lastly, I'm going to divide both sides by 2. And I get -20 divided by +2 is -10. So let's check it, and I'll use the calculator for this one because we got it here. So let's do the square root of 2 times 10, -10, make sure you do that right, -10 minus 7. Uh-oh, not a real answer. Wait a minute, 2 times -10 minus 7, that's the square root of -27. Does the square root of 20, it does, but these aren't going to be real answers, so we're going to say that there are no, and I'm going to use that R to say there are no real solutions. There are solutions, but they're imaginary, and that's a little bit beyond us right now, so we're going to say that there's no real solutions. Since you can't take the square root of a negative, we're going to say that there's no real solutions to this problem. Let's try one more solving problem. We're going to isolate the square root, so first thing we'll do is add 5. 2 times radical x minus 1 equals 5 minus 1 is 4. Now, don't square both sides yet. You got to get rid of that 2. Or you got to be real careful if you don't. 4 divided by 2 is 2. Then, we're going to square both sides. Now that I have the square root by itself, I have x minus 1 equals 4. I'm going to add 1 to both sides, and I get x equals 5. So let's check that. 2 times the square root of 5 minus 1 minus 5. If I plug in 5 for x, I should get -1, and I do, so I did it right. Cool. Last thing we need to be able to do is graph. So the first thing you have to do when you graph is you have to find the domain. And to do that, you take the radicand, x minus 2, and you set it greater than or equal to 0. We're trying to find when it's non-negative. Now, if you add 2 to both sides, you'll have x is greater than or equal to positive 2, which is where we're going to start our table, at positive 2. If you plug in positive 2, 2 minus 2 is 0, the square root of 0 is 0, and 0 plus 1 is 1. So we have our table started here. The first point that I'm going to plot is 2, 1. But I need other points. And I don't want to take the square root of numbers that aren't perfect squares. So I'm going to set the radicand equal to a few nice, helpful numbers. So perfect squares that I know are 1, 4, and 9. And this will help me figure out what I should plug in to take the square root of perfect squares. If I add 2 to both sides, x would equal 3. If I add 2 to both sides, x would equal 6. And if I add 2 to both sides, x would equal 11. If I plug those numbers in, I'll get perfect squares. 3 minus 2 is 1, the square root of 1 is 1, and 1 plus 1 is 2. You might start to notice a pattern, but 6 minus 2 is 4, the square root of 4 is 2, and 2 plus 1 is 3. I bet this is 4, but let's make sure. The square root of 11 minus 2 is 9. The square root of 9 is, well, the square root of 9 is 3, and 3 plus 1 is 4. Hey, it worked. Okay. So let's plot those. 1, 2, 3, positive 2. 0.63, and 11's a little bit off the page, but I'll make it work like that. And when you draw it, it should look like half of a parabola. And you should remember from family of functions that x minus 2 makes the function go right 2, and plus 1 on the outside makes the function go up 1. So this has gone right 2, up 1 from the original parent function, the square root of x, and I can see that because my first point was at 2, 2, 1. One more problem, home stretch. Here I'm giving you the x values I want you to plug in, so you don't have to worry about setting up those little mini equations. Let's plug in negative 3, so negative 3 plus 3 is 0, the square root of 0 is 0. Negative 2 plus 1 is 1, the square root of 1 is 1. 1 plus 3 is 4, the square root of 4 is 2, and 6 plus 3 is 9, the square root of 9 is 3. So let's draw that. Negative 3, 0, negative 2, 1, 1, 2, and 6, 3. So there's my radical function, that's f of x. Again, it's half a parabola, looks like that. I also want to do the same thing with g of x. This is a linear function. So if I plug in negative 3 here, negative 3 minus 3 is negative 6. Negative 2 minus 3 is negative 5. 1 minus 3 is negative 2. And 6 minus 3 is, oops, that's cool I guess. 6 minus 3 is 3. So let's plot those points. And this is a line. You could probably just graph it the old-fashioned way. Start at negative 3 and go up 1 over 1. And I'm going to do that a bunch of times. Got it. Nice. Okay. If it intersects at that same point, that's what we're looking for. When we solve systems of equations, when we solve systems of equations, we're trying to find where the two functions intersect. And they intersect right there. I can also see it in the table. They intersect at the point 6, 3. So when I say solve a system of equations, I want you to plot the two functions and determine where they intersect. And here we're not using Desmos, we're doing it essentially by hand. That's it for solving radicals, guys. If you can do this crash course, then you are in good shape for our test tomorrow. So good luck, and I'll see you later.